Okay. Hi everyone. Welcome to the reading group. So this is going to be the first one of like many, hopefully. So we're here with Ali and Leah. So we're from Entalpic, and we're also co-hosting with AI Alliance. And so this is going to be the first one of the year, and then we have a few scheduled already for January and so on. So yeah, just checked in on LinkedIn the calendar. And today we have Gang, and he's going to be presenting on graph diffusion transformers. If you have any questions, just write in the chat, and yeah, we can like read it out loud for you. Yep, I think all good. Go ahead.
Thank you. So, hello everyone. I'm Gang Liu. I'm from the University of Notre Dame. Today, my presentation topic is graph diffusion transformers in context molecular designers. Molecular discoveries in the chemical space is like finding a habitable planet in the universe. So we can examine the molecular structures one by one to find our target. That's water screening. Water screening requires us to build a prediction model based on the labeled molecules. Then one can screen the molecule in a molecular library. It usually contains billions of molecules. Although it looks like a pretty big numbers, the observable space of the molecule is actually quite limited compared to the whole chemical species. We don't know the exact number that how many molecules may exist, but it has been estimated much larger than the order of 10 to the power of 16. So we wonder, is there a way for us to jointly explore the observable and all the possible molecules? That's the motivation of the university design. In the task of the university design, we input our requirements into a generative model, such as the diffusion models. And the model outputs the specific structure to meet the desired properties. For example, give this task in virtual cellular toxicity against Chinese hamster A8 cell lines. We can prepare our data, train the model, and use the generation model to design a structure that is active to these properties. However, in practice, this one model for one task pattern doesn't scale because there could be millions of tasks or the assays. Here, I present two more examples from the Campbell database. There are assay descriptions about the ADME or the binding. You can see, but you can find from the Campbell statistics, there are millions of such assays. And beyond these drug assays, molecule can make materials. Scientists also want to customize their task. For example, they want to optimize the existing structure of the drugs with new constraints to get something new. So given these challenges, we need to design a new molecular foundation model that can quickly adapt to a new task at the inference time. That's the motivation of the in-context molecular design. In in-context molecular design, we represent the concept of the task by multiple molecule scale pairs. Each pair is one example. We use three kinds of example here. They are positive example, medium example, and negative examples. We find that we use three kinds of example because we find that one type of example is not sufficient to represent the task concept. For example, if two tasks are very similar, they may have very similar positive examples. So we use different kinds example types. It gives us a more comprehensive view of the task. The benefits of this new molecule scale context is that when we switch the context, like by adding or removing examples, we are implicitly changing the task. This example, we call them demos. Like by analog, the large language model uses the sentence as the demos, and we use molecule scale pairs as the demos. Along with the demos, we can input the query scale into the molecular foundation model. Then the model can design the structure based on the demos. building the molecular foundation model.
Can you go back to the previous slide? Etienne was asking a question about what a score represents.
What is power
What
response?
is score essentially, like what does it represent in that case?
Oh, sorry, what does what represents?
When you talk about score, is it?
Yeah, I see. So basically, we think of them as a normalized score between 0 and 1. And so we define the target score as 1, and it's like kind of similarity to the target. I will introduce how can we get score later in some following slides. But you can think of as a property like the target property is 1, and we'll formulate the context. There are some other molecules. They may not have the property 1, but they have like the property between 0 and 1.
Is it common that you always have like something to normalize between 0 and 1, or are there tasks like where it's difficult to find a way to put?
I think in drug-related tasks, like usually it's pretty common, like we have score between 0 and 1. But for some other property, like materials, usually is a continuous space. It could be the original space is much larger. It's beyond 0 and 1. It could be negative. It could be even be thousands. So basically, in that case, you can still do normalization for that. It represents the relative relationship between the molecule to the target.
Right.
It's like you can think, or you can also think of as the soft version of the position encoding. Like in the position, you have a position ID like 1, 2, 3, 4, but it's the soft version, like you can normalize this kind of a relative position to the target between 0 and 1. Yeah. It tells you how similar this example is to the target.
Makes sense. Thank you.
Yeah, thank you for the question. So I go to this page, and this
sorry,
building
before you continue, there's also another question. What do you call a demo in that case as well? Like, because there is demos in the figure.
Yeah, all these examples are demos.
And so demos is like what you have as a context, right? What you want to show.
Yeah, yes, it's a context. It's demo context. All prompts. Actually, you can also use prompts like model. Yeah, all this similar. Yeah. Yeah. So building the molecular foundation models based on the demo defined task is challenging, but it's possible. Because you can see from the Campbell database, there already exist millions of assays. So we have millions of tasks to pre-train the models. We can also augment the pre-training task with material properties. Here we show a few examples. So after pre-trainings, we expect the model can quickly adapt to any new tasks that we maybe never seen before. This task, for example, in here, this figure is customized by the scientist and is fine-tuned some existing drugs. So that is given the context, we can design the structure by learning from the context. So to pre-train the models, we pre-train the models with some new ability like in-class learning abilities, we can get some lessons from large language models. First, the in-class learning ability in large language model is often interpreted as the implicit Bayesian inference. But in large language models, the prompts are sentences. They formulate the task concepts. Large language model extract and understand these concepts to solve the queries. So this kind of magic cannot live with the scalable model architectures like transformers. Previous study also tried to explore that whether in-class learning abilities emerges beyond the language data. So they use the prompt style input label pairs of simple functions. And found that the transformer can also do very well in such scenarios. The third point is that other work found that the distributional properties of the pre-training data is really important. There are two kinds of distributional properties that is very important to the emergence of the in-context learning abilities. They are the Bostinus and the requirements of the query class with many real classes. In short, the pre-training distribution should follow the Zipf's law. it will benefit the pre-training of the transformers. So on the other hand, the inverse molecular design models have been developed.
Before you continue, can you go back to the last slide? Etienne has a question.
Yes. Hello, gang. Sorry, I asked many questions. Can you go back to the previous slide again, please? So on your pre-training set. So what I'm understanding here is that we have a task. We have different candidates for this task, and each candidate has a score that is assigned in regard to the task, right? And so my point here is to understand if you have for each task the same set of molecules with different scores, or if the set of molecules is different from a task to another.
Sorry, can you repeat the question? I don't quite get it. You mean
do you use for each task the same set of molecules with different scores?
They don't need to be the same set molecule. They could be the same set. They could be different set. It depends on like the training set. Yeah.
And what I don't get here is that I have the feeling that the score is the key element. I mean, is a key element here, and is the score? I mean, is it possible to have? I mean, I don't get how you get this score, and if it's computed as a, I mean, in regard with a reference molecule for this task. So is it basically the similarity between all your candidates and one reference molecule for this task that is very good?
Yeah, it's kind of reference. Also, you can think of as the position ID. Like in transformer, typically we have a token input. Here, the token is like we will introduce the token is actually from the molecule structure, and also you have position ID 1, 2, 3, 4. But here is like the position number between 0 and 1. Like it represents the similarity or between the candidates to the reference or to the target.
Because what it means is that basically the reference is the optimal. I mean, if you can go greater than 1, then you can't find something which is better than your optimum in your training set.
Because here that task is pretty a narrow definition. It's a task for the reference. It purely means a task for the reference. So in that case, that should be the optimal.
Yeah. Okay. Interesting. Thank you.
Yeah. Thank you for the question. And then go back to the related work about inverse molecular designs. So there are 2 lines of work. The first is the molecular optimization methods. There are plenty of such methods. For example, Nurix 2022 work called the sample efficiency methods, a benchmark for practical molecular optimization. In this work, it benchmarked more than 12 methods. But usually in molecular optimization method, you need to call the oracle functions. So like a typical setting is like all these methods are evaluated by 10,000 oracle calls. It's pretty expensive actually, and it may not always feasible if you focus on some tasks like require experiments, and it's also much expensive than just prompting the models. And another line of work is the diffusion model for molecules. After several years of development, there is a recent work called the graph diffusion transformer for multi-conditional molecular generation. The graph diffusion transformer, or graph DIT, adapts the scalable diffusion transformer models to molecules, and is promising to serve as the architecture to pre-train the molecular foundation models. So what are the graph diffusion transformers? So let's take a very quick look at these models. Graph diffusion transformer or graph DIT are built on discrete diffusion process for molecules. In the forward process, it defines a transition matrix to perturb the molecular structures based on the joint distribution of atom and bonds. The atom and bond features in the molecule are concatenated in a vector. as a graph level input. So it's compatible with the transition matrix. So by multiplying the transition matrix to the graph level input, you get the noisy. You can use categorical sampling to get the noisy atom types and bond types. So also this new graph level inputs avoid in the denoising process. This new graph level inputs avoids modifying the transformer architecture. As we can see on the right side figure, we use pretty standard transformer architectures that from the diffusion transformer models. It interacts with a foundation vector through the adaptive layer normalization. In this way, we can keep the scalability of the transformers. Okay, now graph diffusion transformer is good, but it has one limitations. So if we want to use them as the foundation model, so because graph diffusion transformer work on atom level representation of molecules. So in each token, the graph level input, you can see it has one single atom type. So imagine these scenarios given a context with 50 tokens. So if we can only process one molecule with 50 atoms. However, we need to encode a very large number of molecules given the context same size of the context windows if we want to do in context learning. So here in this work, we propose the demonstration condition diffusion models, or we call it DemoDiff. Here is an overview of this work. We use a group of the molecule and the scale pairs as demos. They are conditions for the graph diffusion transformers. We add a tokenizer module between the input data and the graph DIT to encode and decode molecules between atom level representation and multiple level representations. So what is multiple level representation? Here the left figure, the bottom left figure give us one example. Here in this figure, each node represents a molecule motif. Looking into the motif, you can see each atom has an index. So these motifs are connected by directed edges. These edges has two attributes. The first attribute specify what kind of the bond types. For example, if it's single bond, it means that when we these motifs are connected by the atoms with single bonds. And the second attribute here specify what's the attachment index in the source molecule, in the source motif. For example, if the index is 0, the directed edges should be attached to the atom 0 in the motifs. So with these motif types and bond types, the graph DIT can concatenate them as a single input for transformers to denoise. During the denoising, the multi-hand attention naturally attends to the demo tokens and learn from the context. The conditions are more naturally integrated into the transformers. Then one can always decode the output of the transformers as a complete molecule using the decoder function in the tokenizers. So how can we get these motifs? So here is a
continue. We have a few questions.
Okay,
and then I have some questions.
Yes, Gang, please could you just clarify? So what I understand from that is that we give as input some demos with their scores, and basically we ask the transformer to design the agency matrix of these demos together so that we end up with a combination of these two demos. I mean, these two conditions that is different.
No, in diffusion model, you can say the diffusion step start from random atom and bonds. So initially this green nodes, it's denoising the molecule we want to denoising, the molecule we want to generate is random in the timestamp t. So this random token and along with demo token, they are included in transformers in a same batch. Just like how language model attend to the word tokens within the same sentence, this kind of like random tokens in the transformers, it attends to the demo tokens and to do denoising. And the denoising process is a iteration process. We gradually refine the random noise tokens to something until to the timestamp 0 until we get something valid molecules like that. Yeah.
So what I understand from that is that you're generating only discrete parameters. I mean, everything is tokenized. And what I don't get is what's your vocabulary? Because I get the feeling that basically the vocabulary was only the agency matrix, but it's not the case.
Vocabulary. The vocabulary is about the motif. You also have the vocabulary for edge types. But the most important thing is that how can we get the motif vocabulary? Given these molecules, how can we decide which bond to break and into different parts of motifs. I will introduce how to get the motif in this page, but in this page, it's just give you an idea what's the motif looks like.
Okay, so what I understand is that we select. I mean, this diffusion process leads to select. A tuple of motifs with their associated agency matrix or connections to other motifs. Okay. Interesting. Thank you for the clarification.
Yeah, thank you. Thank you for the question.
I have another question. So you tokenize the motifs, and what do you do with the score to put it in the context? You just put the value, and
you mean the score? The score is attached to the entire molecule. So it's just like the position ID. You can process in our model. We process it as how we process the position ID. Each token has we get an embedding for that score and then add the score to the token embedding. Yeah.
Okay. So
and also we use the rope. And also we use the adaptive layer normalization to process that kind of score to give condition as condition. Yeah.
Thank you.
Yeah. Thanks for the question. This page tell us how we get the motif vocabulary. This algorithm we call is Node Pair Encoding. It's pretty similar to the Byte Pair Encoding, but we adapt them to the molecular graphs. So given the input here is a molecule, a data list of molecules it's D, and also here the initial vocabulary is empty, and the user can specify what size of the vocabulary they want to have, and also they also input another hyperparameter is the ring count threshold. I will introduce what's that. What's n? We'll use how to use n here. Here in the second line of the code, we first need to count the frequency of the rings across the molecule list. So here we want to add the ring count strings to this Node Pair Encoding. So that for each of the rings, it either a complete motif added to the vocabulary, or it represented only by the atoms. Why we want to do that? Because we don't want to break rings into two motifs. It will introduce ambiguity between how can we connect these two rings. How can we connect the two parts of the rings? Because if we break two rings, we introduce at least two attachment positions for each of the motifs. That's what we don't want to have. So here, to initialize the vocabulary, we first add all the elements in the periodic tables. Also, for polymer materials, we add the polymerization, the wildcard symbol to the vocabulary. We also add the top n frequent rings to the vocabulary. Then we can initialize the process by repeating the merging neighbor and frequencies selection and update graph. These three steps. So from line 5 to line 13, we can see that these steps merge to neighboring motif and get their counts. Then from in the line 14, it selects the most frequent motifs and add this motif to the vocabulary. Then from the line 15 to the line 23. So basically, this step updates the representation of molecules in the molecule list after we get a new after we get the new motif and after we select a new motif and add them to the vocabulary. Yeah, we repeated these 3 steps and until the size of the vocabulary is achieved. That's the algorithm. And also, so after we set up the algorithm, we began to prepare the data. We collect data from many different sources. So that typically the experimental molecules. For example, we use the data from the Campbell database. It contains millions of drug-related assays. Also, we collect polymer data from for the material properties. This property include something like melting temperature, the gas transition temperature, the thermal conductivity. So, in summary, we get around 1 million molecules, and there are more than 155,000 unique property types, and totally we have around 1.6 million of tasks. So to formulate a task, we use one label as the anchor and compute the similarity between it and other labeled molecules. These similarity scores are calculated based on the property values. So we set the anchor molecule as a target. It has the target score 1. We keep the similarity between the molecule and the target. We group molecule based on the similarity scores as into 3 categories. Some are molecule, including the positive molecule, medium molecule, and negative molecules. So then we sample up to 15 molecules in each category. So basically, on the left figures, we can see the property rank versus the frequencies in the pre-training data set. So generally, we can see that the distribution follows the Zipf's law, so with long tails. So it gives us confidence that we have similar distribution like the language data has. So to pre-train the foundation model for molecules. Yeah. After we train our tokenizers with the unit training data, here the last figure is a comparison of the atom level representation and the new multiple level representations. So here we set the vocabulary set to be 3,000, and we consider only top 300 rings. So then we run the Node Pair encodings on the pre-training data to get the motif vocabularies. All these motifs are chemically valid. We preliminarily define a set of commonly functional groups, and we find that almost all of them are covered in the vocabularies. So to compare this, our motif vocabulary with some existing heuristic methods like breaking the retrosynthetical interesting chemical substructures or BR breaks this algorithm. We also apply this algorithm to the same pre-training data set. This algorithm gives us like more than 120,000 fragments. And but we found that 98% of them appears only 100 times. Remember that we have more than 1 million of molecules. Yeah, and around 60% of them of this fragment only appears once. So they don't very efficiently leverage the frequency in the pre-training molecules. Also, we found that the NPE algorithm can actually cover the most frequent motifs found by the breakers algorithm fragments. So here, for example, we examine the top 100 breaks fragments. I found that 89 of them actually are covered by the NPE algorithms. Okay, after getting the vocabulary, we can begin to pre-train the models. That's pretty standard. Like we pre-train the model on using around 146 H100 GPU days. So basically, then we evaluate the model across 33 tasks. These tasks include the drug rediscovery, drug multi-property, objective optimization, structural constraint design, drug design, target-based design, and material designs. So basically, these tasks come from very different sources, and I list the relevant paper here for reference. Yeah, each of the tasks generally has a computational oracles. They are either a computation function, a machine learning model, or docking software. This oracle are used to evaluate the generated molecules, where here is better. Also, for each task, we prepare up to 150 label examples. They are used for different purposes, like training the prediction model, because some of them baselines I will introduce later need to use prediction models. And also we use this example to formulate context for in-content learning baselines. Yeah. Okay. Then let's go to the results. Here are the results. We compare the DemoDiff with 19 baselines. There are 6 molecular optimization baselines. They require the call of the oracles. So we limited the number of oracle calls as 100 because for other methods, we don't require any oracle calls. So we also examine these methods, like if we replace their oracle calls with some prediction models, whether they still have good performance or not. But generally, we find that performance degrade. Yeah. Besides, we compare the DemoDiff with 2 conditional generation models, and also we compare the DemoDiff with different large language models. For closed source large language models, we directly call them with in-content learning examples. Also, if they are open source model like the Llama 3.1, like Q13, they are 8 billion. The open source model with 8 billion parameters, we can fine-tune them at first with the same set of the molecules used in our pre-training. And also, then we use in-content learning. We prompt them with the same context, with the in-context examples. Yes. Here, from the tables, the reported scores measure the top 10 generation quality by the harmonic means of 2 scores. One score is the average oracle score across 10 examples. Another score is the internal diversity scores. So we hope this number can report the balance, how different models generate molecule by balancing the diverse and hit. By balancing the diversity and hitting. Yeah. So basically here we group this. In this table we report the mean and standard deviations across different task categories. Yeah. So compared to
there's a question.
Okay.
Yes. How do we fine tune this kind of LLM on this task?
Sorry.
How is done the fine tuning on this kind of task for LLM?
We fine tune 2 LLMs. One is Llama 3.1. The other is the Q13 8 billion. Qwen 8 billion. Yeah. If you find this fine tune FT, it means the model is fine tuned.
Yes, but I don't get. I mean, so we are asking the LLM to design molecules that looks like the context basically, or you give them the scores and the molecules and asking to design a new one. But with what kind of vocabulary do you design such a molecule with LLM?
Just use the original vocabulary. Like each language model has their own tokenizer, has their own word vocabulary. So I just use that.
Okay.
Do you use smiles as input?
Yeah, it smells. Yeah, smells.
Okay, interesting. And yeah, I was curious about why did you choose to basically use a diffusion transformer and not a regular GPT transformer?
GPT transform.
I mean,
yeah.
Why not just a regular generative transformer in an autoregressive manner?
You mean which
what
method?
is what is adding the fact you're having some diffusion in the process, rather having just a supervised task with the same dataset and generating your
I'll say that's a difference between diffusion model and autoregressive modeling for molecules. Like generally, if you want to autoregressive molecule, you need to define which fragment to generate first and which fragment to generate next. So we don't actually, a diffusion transformer is that it's like an autoregressive in another space. It's like we generate a molecular structure, all the part of the molecular structure directly, and then we refine this structure aggressively. That's kind of autoregression. You can think of that kind of autoregression in different space. So basically, we prefer the later because we don't want to decide which fragment to generate first. The molecule don't have such a prior. So we don't want to define that. So we choose diffusion. Yeah.
Interesting. Thank you.
Yeah, thank you for the question. Yeah, basically, from this table, after we introduce the setting, so from this table, we can see some numbers. Compared to this baseline, we find that DemoDiff is ranked at 4.1 positions on average, and the second baseline is ranked around the 7, like so. Except for the drug rediscovery task and the structure constraint task, so DemoDiff outperforms all the other 19 methods. So for the average task scores. Yeah, that's about the table. And then in ablation studies, we evaluate 2 settings for DemoDiff. One is the context length, and the other is the ratio of the positive examples. So from the first figure, we found that in general, as the context length increases, so the model performance gets better. It indicates that when we have more examples, we can better represent the task concept and the model can perform better. And also, from the second figure, we see that to define the task concepts, we should mix the positive, medium, and negative examples. But because, for example, if we use pure positive examples, and it didn't give us the best performance. Instead, if we only use half of the context window to include the positive example and use half of them to include other examples, it can give us better performance. Yeah, because we think of this reason is because that we can better represent the task concept to the target. Yeah, in case studies, we also first tested whether DemoDiff can design positive molecules based on all negative demonstration demos. Here are 3 examples in different task categories. The first one is the structural constraint design, and the second one is the drug rediscovery, and the third one is the target-based designs. So we can say in the first case, we use 17 negative examples. All their scores are below 0.5. Actually, they're pretty small. Yeah. But we still like this can still, if their number are sufficiently large, we can still use them to represent a task concept, and then the model can learn from such concept to generate some positive examples. So it indicates this kind of observation indicates very interesting future directions. So one can continue increasing the size of the context windows and to pre-train the foundation models with more negative examples. Yeah, it allows us to maybe help us improve the enhanced learning ability of the molecular foundation model to better hit the targets, even in the scenarios where the positive examples are very rare or totally missing.
Sorry, I have a very simple question. For the context window, do you fix it like before training the model? Or is it something that you can increase, like you train a model and you can increase or decrease it?
We fix the maximum context window. Like for example, we fix it to the maximum one to be 150 tokens. But the practical context window can be like flexible. Like you can only use half of them to include examples. Yeah.
Okay, makes sense. And ideally, like you want a context window as large as possible to put like a full data set inside, right?
Yeah. Yes.
Okay. And Etienne, you have a question?
Yes, my question is maybe very weird to you, but as a baseline, did you try to do the same, but for each task, you don't get your context embedding from your scores and molecules, but just with a BERT embedding of the, natural language query associated with the task? Is it a baseline that you try to measure and then try to see how the context learning made the model far from this baseline?
Sorry, I didn't quite get what the baseline you mentioned here is like for a baseline large language model.
Yeah, so basically we get some context through this tokenization of these cores and molecules, which gives a very good baseline, very good context for the model to design a new candidate. But what if you just give us context, an embedding of basically the text associated with the task? Can you get here some results just with that, or it's not enough? And because it would be a kind of baseline in this task.
You mean
not to leverage
embeddings? Get some embeddings of what embedding?
Because each task is associated with some text. We could give a description of the task, a textual description of the task, right?
Yeah. We don't have that in our model. We don't have that in our model.
Yeah, I do understand that you don't have it, but did you try to have it? And then it's a kind of baseline because this is the easiest context that we can give to the model, and see how it improves with the in-context learning.
Okay, you mean given the context, the description of the task in our model or in language model?
Did you try to do it?
In our model or in language model, we don't try to do that.
Yeah,
because in our model, because our concern is that definitely we consider using the text description for the task, but our first step is like can we use the molecule score context, because it's just the first step to build a foundation model, and also we definitely that's a good direction we want to explore in the future. And also in language models, for comparison, we don't use that kind of task. We don't use pure textual descriptions in language model. Yes.
Okay, because it would be interesting to see how if you start from just textual description of your task and then you add some examples about good and bad molecules for this task, see how it does improve the performance of your model. Because basically, I would say the V0 of this model would be with textual description, which is very easy to get.
Yes, that's really good idea. Yes, sure. I think we can explore that. Yeah, thank you for the question. And also the last case study is we visualize the diffusion trajectory, in one task for drug rediscoveries. So basically, we sample 5 intermediate diffusion steps and score with them with the oracle. So the oracle computes the similarity between the generated molecule in the diffusion process and with the ground truth. So basically, an interesting observation is that we can see we label the score in each steps. So generally, we can observe that the DemoDiff can gradually refine the molecular structure to be valid and close to the target properties. Okay, that's that's about the work.
The previous slide.
Uh-huh.
So here, like the ground truth is something that's in the data set, or like how do you know that's the ground truth for the score?
Yeah. Because this task is defined on this structure. This task is called drug rediscovery. So the ground truth is the drug. This is a drug structure. So basically, someone defined this task like, can you optimize this drug structure with some additional constraints like that?
Okay, so for the context you give it, like this is the only structure you should get with how the task is defined, essentially. Like it means that if you have that context that you specifically give in the prompt, the only molecule that you should get is the ground truth, like the expected.
That's a good question. Generally, I think maybe I need to recheck about the function. But I think the ground truth is not like a ground truth. Maybe it's not accurate. It's something like a reference. Like if you get a 1, the score 1, it means that just repeat that structure. So that doesn't make sense. Like, I think because it's really sorry, it's find something different. But you still need to get some similar to that original structure. Yeah, I need to recheck about the original task definition for that. Yeah.
Okay, thanks.
I have a question. So just to understand better how the training of this model is done, I think that this slide is good. So let's say you start from step 300, and you go back to step 200 at training time. So you add some noise to your vocabulary tokens, and then you try to predict the noise that you added on this vocabulary. So the noise you are adding from the noising step to another is on the vocabulary tokens. Is it right or is it wrong?
The noise here is like noise. We define the noise as a transition matrix. Basically, when you add noise, you get some different motif types in the vocabulary. Yeah.
So basically, the noise that you add has the same shape as your vocabulary. The noise tensor.
Let's go back to this page. Can you see this page? So basically, here in this page, this is how graph DIT and noise on the atom level. Basically, you can replace the atom with a motif in this figure. Like the noise is like here is like motif to motif noise, and here is like the bound is like edge to motif transition matrix. Basically, generally that's a shape of noise. So basically, you can save the noise as here is this dimension is the number of motif types. It's 300. It's 3,000 in our because we define our tokenizer. We define our tokenizer has a vocabulary size to be 3,000. So it's 3,000. And here is like the bound type. Actually, we focus only on the bound types. So there are 3 bound types. Single, double, triple, and then we also need to set a hyperparameter for the maximum token we want to consider in molecules. So basically, I remember this number should be the maximum one should be 50 or 30. Maybe 30. I think. Yeah. So basically, it's like the 3 times 30.
Okay, so basically you're masking the bonds that you can draw between atoms at each denoising step, or you're unmasking that. Basically, you're designing new bounds at each step.
And designing new
I'm
bounds.
not sure I do understand what the noising process looks like. It's a bit. I mean, I think I need an example to deeply understand that, but it doesn't matter. Don't worry.
Yeah. Okay, that's good question. Generally, I think the idea is like you predict in each step. It's like the predict of the it's like two classification tasks in each step in denoising process. Like you use transformer to predict the motif type. I use this transformer to predict how these motifs are connected. This edge type. So basically, they are here for each edge. They have two properties. So the model outputs two edge attributes. One is the prediction of the bond type classification or direction, or attachment index classification. This you can think of the transformer has three outputs. Like one is the motif type, one is the bond type classification, and the other is the attachment index classification. And then with this information, you can like decode this kind of motif representation to the molecule. So by adding noise, if you are curious about adding noise, it's like given this this motif type, you apply the transition matrix, you get a new kind of motif, this noise, and also for this edge, you apply for the edge type, you can also apply the same transition matrix. I also apply the noising for the bond type, so you can get a new bond type. So usually the tokenizer cannot decode this noisy structure into the original space because it didn't make sense as a valid molecule. Yeah, so here you can see there's no connection between motifs because although the tokenizer try to reconstruct the complete molecule, sometimes they fail. So you just see a few motifs showing here, but you don't get their bonds. Does that make sense?
Not really, but I'll try to understand it later. Thank you.
Okay. Thank you. Like I just have one page, so I just finished that, and you can, if you want, you can ask more questions. So basically, here I want to share a few takeaways. First, we show that in-context learning ability are not the unique properties in the large language models. It's also a property that emerges from the large-scale data with proper distribution, scalable model, and with sufficient computing time. Yeah, DemoDiff and in-context molecular design are another cases where in-context learning emerges. It's very promising to continue this line of study to research more domain-specific in-context learning or domain-specific foundation models compared to pushing large language model as the universal foundation model across all domains. Domain-specific models can have better performance on many tasks in that domain, and also it need fewer parameters and to achieve comparable and even better performance. Okay, that's all I want to share today. Thank you for listening, and I'm happy to take any remaining questions.
Thank you so much. I have one actually. Did you try to do an ablation study on the number of data sets you use when pre-training? Like, do you actually see that adding more pre-training tasks help generalize?
Oh, that's a good question. We don't have that ablation like by adjust the number of pre-training tasks. We only have ablation like by adjusting the number of parameters. Like we will have a smaller model or medium-sized model or bigger model. Because here the result I presented is based on the 0.8 billion models. So we have other model like only with 70 million parameters with like I remember the 140 million parameters, and then so we find that by increasing the model size, the performance and gets better.
Okay, I was asking because it seems to me that what you're trying to build here is a foundation model that understands like chemistry across very different tasks. So I would assume that adding more tasks that are different could help generalizing.
Yeah. Actually, this kind of idea is validated in other domains in language data. Like as when we talk about the related works, I talk about that. Many related will find that, like here the distribution property. Many related will find that by adding more tasks, even these tasks are very rare. Like it's very helpful for pre-training the foundation models. But generally we take this kind of conclusion or observation, and I think it holds as well for molecule, but we don't do experiments to verify this.
Thanks. Are there any more questions? Okay, I guess not. Again, thank you so much for agreeing to present.
Thank you.
Super interesting. Yeah, we'll upload the recording to YouTube, and I guess if they have any questions, they can reach out to you.
Thank you.
Awesome. Thank you so much.
Thank you very much.
Thank you. See
Bye.
you.